Okay, imagine this. A refrigerator in your kitchen, but it's like totally silent. And not just that, it cuts its energy use basically in half. For years, that's really felt like science fiction, right? But today, we're doing a deep dive into a genuine breakthrough. It's from the Johns Hopkins Applied Physics Laboratory APL and Samsung Research, and it's making that exact future seem, well, pretty real. So our mission here is to really unpack this innovation. We're going to explore these new materials. They're called Shi-E-Wei. What are they? How do they work? And why are they potentially set to revolutionize everything from your home appliances right up to global energy use? This isn't just a small step. It feels like rethinking cooling entirely, addressing this huge global need for more sustainable, efficient ways to do things. I'm actually really excited to walk you through this.
And it really is a critical moment for something like this. I mean, when you step back and look at the big picture, the scale of cooling tech in our world today it's just staggering. Keeping food safe, preserving medicines, preventing massive data centers from melting down. The demand is just constantly going up.
Right.
Population growth, cities expanding, all our advanced electronics pumping out heat. It all adds up. So this innovation, it's not just about a quiet fridge for you. It's about finding a truly sustainable path forward for a fundamental global need. We just can't keep going the way we are.
Yeah, that makes sense. Which kind of brings us right to the problem, doesn't it? Our fridges, our AC units, they've been around forever, basically working the same way. So what's actually wrong with how we currently keep things cold? Why do we need this new approach so badly?
Well, you're right. Those traditional compressor-based systems, they're everywhere, and they work. But they definitely have some significant downsides, things we've maybe just gotten used to. First off, they're bulky, that whole compressor unit. Takes up a lot of space, limits design, And crucially, they are energy hogs. They consume huge amounts of electricity. Just think about every fridge, every AC, every server farm, all running, drawing power constantly. Then there's the environmental side. They rely on chemical refrigerants, things like HFCs, CFCs in the past. If those leak, they can be really potent greenhouse gases, big climate impact.
Yeah.
And of course, that sound, that hum or buzz from your fridge or the AC kicking on and on.
Oh, yeah, that familiar sound.
That's the sound of moving parts. Friction, energy loss, basically.
Yeah.
So the big question is, how do we meet this rising global demand for cooling without making the energy environmental problems even worse? It's a massive sustainability challenge.
Absolutely. And it's exactly because of those challenges, the energy use, the environmental concerns, that this other idea, thermoelectric refrigeration, has always seemed so promising. So let's talk about that. What exactly is thermoelectric cooling, and why hasn't it, taken over the market before now?
Right. Thermoelectric cooling is. It's actually quite elegant, fundamentally different from the compressors and pumps we're used to. Instead of all that, it transfers heat using electrons moving within special semiconductor materials. You can almost think of it like a solid-state heat pump. You apply electricity, one side gets cold as it pulls heat away, and the other side gets hot as it dumps that heat. It's called a Peltier effect.
Okay.
And because it does this electronically, you completely eliminate the need for moving parts or those chemical coolants, which immediately gives you some really nice advantages. These systems can be incredibly compact, much more flexible design possibilities.
Right. No bulky compressor.
Exactly. They're quiet, no motor noise. They tend to be very reliable and long-lasting because there aren't parts wearing out.
Yeah.
And of course, they're environmentally sustainable. No harmful refrigerants.
Okay, that sounds almost perfect. So why aren't our houses cooled this way already? What was holding it back? What were the barriers?
Yeah, that's the million-dollar question, isn't it? Despite that theoretical promise, the traditional bulk thermoelectric materials just weren't very efficient. They couldn't move enough heat effectively to be practical for bigger jobs like a full-size fridge or your home AC system.
Ah, okay.
Their heat pumping capacity was just too limited, and maybe the biggest roadblock for really widespread use. They weren't easily compatible with standard semiconductor chip manufacturing.
Right, the way we make computer chips and things.
Precisely. So that kept them stuck in really small, low-power applications, like those little portable drink coolers, maybe some niche medical devices. But not the big stuff. The basic idea was sound, but the materials themselves weren't good enough, and you couldn't really make them cheaply at scale.
So the potential was always there, quiet, green, efficient cooling. But it was sort of stuck in low gear for decades because of those material and manufacturing limits. It's like having a great design but no way to build it properly. Which is exactly where this story gets really interesting, because APL and Samsung seem to have smashed right through those roadblocks with chess. So tell us, what exactly is chess?
Okay, so CHESS stands for Controlled Hierarchically Engineered Superlattice Structures.
That's a mouthful.
It is. But the name actually tells you a lot. These are high-performance thermoelectric materials that are nano-engineered. That means they're designed, like literally at the atomic level, to be incredibly good at moving heat. This isn't just tweaking old materials. It's a fundamental leap in how these materials are structured.
Nano-engineered.
Yeah, developed by the scientists at Johns Hopkins APL.
Yeah.
And this is really important. The results were rigorously tested and validated with refrigeration engineers over at Samsung Research. That collaboration ensures these aren't just lab curiosities. They're robust and work in the real world.
Okay, that nano-engineered superlattice part sounds fascinating. Can you give us maybe a slightly clearer picture of what nano-engineered actually means here? Are they like layering different materials atom by atom to build a heat superhighway?
That's a great way to put it. A heat superhighway. Yes, essentially. Think about how engineers design complex systems, like that highway analogy. A superlattice is similar, but we're talking nanoscale. Scientists are layering different materials, sometimes only a few atoms thick, in a very precise repeating pattern, like building with atomic Lego bricks.
Wow.
This hierarchical engineering lets them control exactly how electrons, which carry the heat, and phonons, which are like packets of heat vibration, move through the material. They can basically pave the way for electrons to flow easily, carrying heat away, while putting up roadblocks for the phonons that try to conduct heat back the wrong way. This precise atomic-level design is what gives chess its amazing performance.
That's incredibly clever. And you mentioned this wasn't something they just stumbled upon. It has quite a backstory, right? A decade of research, starting in national security, even winning an R&D 100 award. How does that journey happen?
Yeah, it's a really cool example of how fundamental science can lead to unexpected places. The C-chess work started over 10 years ago at APL. Initially, the focus was on solving really extreme thermal management problems for national security.
Like what kind of problems?
Think about equipment that has to work perfectly in incredibly harsh conditions, extreme temperatures, rapid changes, or maybe super-sensitive electronics packed into tiny spaces generating tons of heat.
Okay, situations where normal cooling just wouldn't cut it.
Exactly. High stakes, where failure isn't an option. That kind of pressure really pushed the boundaries of material science, demanding thermoelectric devices with unprecedented efficiency and toughness. Then came the realization, the aha moment, that the principles they developed for these extreme cases could be adapted elsewhere, like using precise, gentle cooling for medical prosthetics to make them more comfortable for users. Winning the R&D 100 award in 2023 really highlighted how versatile and groundbreaking it was. It shows how investing in that deep science pays off in ways you might not even predict initially.
And the results from that journey, published in Nature Communications, they really are something else. At the material level itself, nearly 100% better efficiency than the old thermoelectric materials. At room temperature, about 80 Fahrenheit, 25 Celsius. Then when they built actual modules with CHS, almost 75% improvement in efficiency. But here's the kicker. In a full working refrigeration system tested under realistic conditions, a 70% improvement in efficiency. Those aren't small numbers.
No, they're absolutely huge. And that 70% figure, the one at the system level under practical conditions, that's the real headline grabber here.
Right.
I mean, just try to imagine for a second, what would a 70% efficiency jump mean if, say, every fridge in a big city adopted this?
The energy savings would be enormous.
Exactly. You might avoid building new power plants entirely. You'd see a significant drop in carbon emissions nationally, even globally. It's not just saving a few bucks on your electric bill, it's potentially reshaping energy demand on a massive scale. Rama Venkata Subramanian, he's the lead researcher, he summed it up perfectly. He said, it marks a significant leap in cooling technology and sets the stage for translating advances into practical, large-scale, energy-efficient refrigeration applications.
And you mentioned that validation with Samsung Research. That seems critical. It's one thing to get results in the lab, but having a giant like Samsung confirm them, what did that actually involve? Why was it so important?
Oh, absolutely crucial. Samsung's engineers didn't just, nod along. They worked closely with APL. They did detailed thermal modeling. They meticulously calculated heat loads, thermal resistances, all within the designs of actual refrigeration systems.
It's really putting it through its paces.
Precisely. They wanted to evaluate performance under real operating conditions, not just perfect lab scenarios. That validation is what gives everyone confidence. It proves these gains aren't just theoretical, they're achievable in products you might actually buy someday. It bridges that gap from science project to potential market disruption. Builds huge trust.
Okay, so the efficiency is incredible, it's validated, but let's talk brass tacks.
Yep.
What's the biggest hurdle left? Is it cost? Getting it integrated, just changing how the industry works. And crucially, can they actually make this stuff affordably at scale? Because amazing efficiency that costs a fortune won't solve the global problem, right?
That's exactly the right question to ask. And honestly, this is where She-S seems particularly well positioned. It tackles several hurdles at once. This isn't just a lab trick. The She-S technology uses thin films, and it needs remarkably little material. We're talking 0.003 cubic centimeters per unit.
Tiny. Like a grain of sand, you said?
About that size, yeah. So this massive reduction in material is key. It means you could potentially mass produce these things using the same kind of tools already used in semiconductor manufacturing. That's the pathway to driving down costs significantly and making widespread adoption feasible. It directly addresses that cost barrier you mentioned.
And they're using an existing manufacturing method too, right? Which helps with cost and scale.
Exactly right. They use a process called metal organic chemical vapor deposition, MOCVD for short.
MOCVD.
Okay. For anyone not familiar, think of it as a super precise way to spray paint extremely thin, perfect layers of material onto a surface, almost atom by atom.
Like molecular spray painting.
Sort of. It allows for those intricate nanoscale structures that make chess work so well. But the brilliant part, MOCVD isn't some brand new experimental technique. It's already a workhorse in industry. Well-established, scalable, cost-effective. It's used right now to make high-efficiency solar cells and LED lights commercially.
Ah, so the infrastructure kind of already exists.
Largely, yes. John Pierce, an engineer at APL, pointed this out. MOCVD is already widely used commercially, making it ideal for scaling up chess production. That's a massive advantage for getting this out into the world. Removes a huge potential bottleneck.
So where does this lead? We're not just talking tiny coolers anymore, are we? This sounds like it could scale up significantly, maybe like we've seen with other tech breakthroughs.
Yes, the vision, absolutely.
Yeah.
Venkat Subramanian made a really good comparison to lithium-ion batteries.
Okay.
Think about how they started small, powering phones and laptops, and then scaled up massively to electric cars, even huge grid storage systems. Chess thin film tech could follow a similar path. You start with smaller refrigeration units, maybe specialized cooling, then potentially grow to support entire building HVAC systems.
Wow, silent, super efficient air conditioning for whole buildings.
Exactly. It could fundamentally change how we design buildings, how cities manage energy. When you look at the big picture, that scalability, that manufacturability, it's just as important as the raw efficiency numbers. It's what makes the real-world impact possible for you.
That's a game-changing vision. But wait, there's more to it than just cooling, right? This
Yeah.
isn't only about fridges and AC. What other amazing things could chess do?
You're absolutely right. The potential goes way beyond just making things cold. These same chess materials have this incredible flip side. They can do the reverse. They can take a temperature difference, even a small one, like your body heat, or a waste heat from electronics, and turn it directly into electricity.
Whoa, okay. Energy harvesting.
Exactly. Energy harvesting, turning wasted heat into useful power. It opens up a completely different set of possibilities, really pushing toward energy independence in unexpected ways.
That is amazing. So generating power from heat, we normally just ignore. What kind of truly mind-bending applications could that lead to?
Well, think about next-generation sensors or tactile systems. Advanced prosthetics that aren't just smart, but maybe even powered by the wearer's own body heat.
Self-powered prosthetics.
Yeah. Or imagine smart sensors built into bridges, roads, buildings, maybe even inside your home that never need their batteries changed because they just sip power from the ambient temperature changes around them. And beyond that, Jeff Moranchi at APL mentioned it could enable scalable energy harvesting for everything from making computers more self-sufficient, reducing their power draw, to even powering spacecraft.
Yeah.
Yeah, places where generating power reliably and efficiently is absolutely critical. These were applications that were just, well, science fiction with the older, bulkier thermoelectric materials. It really shows how one material science breakthrough can ripple out into so many different fields.
And it sounds like APL is still pushing forward. They're not stopping here.
Not at all. They're working to refine SHEs even further, aiming for efficiencies that could rival traditional mechanical systems even in tougher jobs, like freezers, which need much colder temperatures. They also want to demonstrate larger scale systems. And this is pretty cool. They're looking at integrating AI methods to really optimize energy use in complex cooling systems, like distributed cooling in buildings or data centers. It's this exciting blend of materials science and intelligent control.
Okay, so let's wrap up this deep dive on chess. We've looked at what feels like a genuinely revolutionary step in solid-state cooling. These nano-engineered materials promise incredibly quiet operation, huge jumps in energy efficiency, and a much greener approach by ditching compressors and chemical refrigerants. But it's also got this fascinating dual-use harvesting energy from waste heat, with potential applications from tiny personal tech right up to massive infrastructure. Just picture it. Your home appliances, the data centers powering the internet, maybe even your gadgets all running silently, using far less energy, with a smaller carbon footprint. This really does paint a picture of a future where innovation makes things smoother for us, but also much more sustainable. That potential shift in energy use and generation feels huge.
It really does. And maybe just one final thought to leave you with. Think about how breakthroughs like CHS start to challenge our basic ideas about energy. If our own bodies, our devices, even the heat pouring off equipment, if all that can become a power source, what new possibilities does that really open up for you, for society? It makes you see energy not just as something we consume, but maybe something we can capture and reuse from almost anywhere. A truly different way of thinking about our energy future.